The question is, what is algebraic geometry? Now, algebraic geometry is nothing but the study of zeros of polynomial equations. You can see this in entire number theory, where we try to find integer solutions of curves, for example Fermat's last theorem, or just rational points on different curves, and so on. So let us write this down. So algebraic geometry is nothing but the study of zeros of polynomial equations, or you can say the solution set of polynomial equations. So let us draw some of these polynomials. So let me first draw the x and y axis, and now I will draw the polynomial in a different color. So this is just, you simply trace, we are tracing a polynomial in the complex plane. Now it looks like a R2 plane, but you should think in C2. So we will write the polynomial down. Notice that I'm saying complex, not real plane. The objective of this course is just to study over algebraically closed fields. Now let us draw another polynomial. This is all very familiar. This is nothing but a circle, and we write the corresponding equation. Yeah, so the circle drawn on the plane is nothing but the solution set of the equation. So the things which we are cutting out by these equations are the solution sets. The third I will draw is a parabola. Again, the corresponding equation is this. Now, the purpose of algebraic geometry is that this is what these equations represent in geometry. Now I want to make this clear. We are drawing these figures in R2, but you should think of this is in C2. Okay, so now with this equation we want to associate something which we will call the regular ring. So we want to associate with geometry some algebra. So you take the corresponding ring to the entire plane, and you modulo out the figure. Now obviously the figure is 0 in plane. In the rings it is also 0 as you take it R over I, where I is an ideal. So we are constructing new rings. Now notice that these are called algebras of finite type. So again we write it like this. Yeah, so you modulo out with the ideals. So this is the correspondence we want to build. So this we will call as ring of regular functions associated with the particular polynomial, which we will call a variety. So again I will write it. So we focus on algebraically closed fields. So we will come back and construct all these bridges which we have just mentioned or said in passing later on. So our purpose is simply to focus on algebraically closed fields. So we are focusing on algebraically closed fields, for example complex numbers, algebraic numbers, the completion of finite fields, or the algebraic closure of finite fields in fact. So you should check out the definition of algebraic closure on Wikipedia and see the examples there and see how to construct an arbitrary algebraic closure for a field. So notice that this field of algebraic numbers is strictly contained within complex numbers. So closed fields we are going to denote by this small letter k. So on this slide we talk about affine n space over a algebraically closed field K. So affine n space is nothing but a tuple. So you can think of it as, say, for example, Cn, you take n numbers. So yeah, there is nothing else to say here. It's just an n tuple. So we write it down. So each of these elements xi belongs to the algebraically closed field K. So the idea is to consider subsets of this. So we want to consider subsets of this. So why are we not writing it as Kn is because we are attaching special meaning to it, and as sets are different, and we will see it how they are different. So we consider S as a subset of this affine n space, and this subset is closed, and we sometimes call it as algebraic set or affine algebraic set. Yeah, if it can be written as zero set of polynomials. So that is, it is a zero set of polynomials means that all the polynomials vanish on this set S. So the set S is closed if it is a set where some polynomials vanish. So in some sense it is a solution set of these polynomials. So in the previous slide we saw we had drawn out the set S from a single polynomial, and now we are talking about a set of polynomials and they have coefficients in field K. So let us write this down. So again these are nothing but tuples. Yeah, these are again n tuples, but these n tuples are such that there are some set of polynomials which vanish on these sets. So on the previous slide we had drawn a single polynomial, now we are writing multiple polynomials. There could be infinitely many of these. So yeah, so we could have infinitely many polynomials like this, and all these polynomials vanish on the set S. They all become zero on the set S. So these are common zeros of polynomials. Now what is the closed set of A1? So we have to discuss now some examples so as to make the ideas more concrete. So we want to talk about closed sets of A1. So first of all, it is all of A1 because 0 equals to 0 is again a polynomial equation. It is defined on the entire line. So we call this A1 just a single element, a single tuple as affine line. So it is defined by 0 equals to 0. Yeah, it vanishes on the entire line. So all of A1 is closed set. B, finite subsets. So finite subsets of AK1. Now notice that you can write a polynomial since K is algebraically closed field. It splits like this. So the solution of this equation A1, A2, A3, A4 all the way to AN represents the closed set. Now notice that even if you add infinitely more polynomials to it, the solution set will not exceed this A1 to AN. Obviously, after all, fx has to vanish. So if you add certain more points, then fx will no longer vanish on it. So if you continue adding more polynomials, you start with a single polynomial in your solution set S and you continue adding more polynomials to it. Now if you continue adding more polynomials to it, most likely you are going to decrease the solution set which was A1, A2, A3 all the way to AN. You're most likely going to decrease it because other polynomials also have to vanish on it in addition to fx vanishing on it. So this is important to consider. As you add more and more polynomials, you're actually decreasing the size of S. So so let us now come to A2. So that is the affine plane. Now we have I've told you before, you can also think of it as a picture over complex C2, complex plane. So you first start with A, 0 equals to 0. So all of the plane is a closed set. Again, we will copy B as it is, finite number of points. So in fact, all points like x minus a1, so you can have these points which also form closed sets. And we have this addition curves. These curves, like in the previous slide, we had cut down curves in the plane. Similarly, we have here. So let us draw this figure. Yeah, so this figure is just to make sure we understand the stuff. So figures are like this. This is a curve, set of points, and then I draw another curve. I draw another curve. So I've drawn 3 curves here and a set of points to show that these are the closed sets of A2. Similarly, I draw the finite number of points for affine line. Now what are the open sets? Now you see open set is huge. They're just like you take the complement of the closed sets and you get open set. Now if you see the complements, they are huge. Now this will be more clear. Let me write this down here first. So open sets are huge. So let us write down the open set here also. Draw a different figure. For A2, we're going to draw a circle first. So this is a circle, this is a closed set, and the complement of this set is open. So look at the open set. So this is huge. Everything which does not lie on the circle is open, so which I have just shaded with lines. So interior of the circle, exterior of the circle, this is all open set. Now consider another curve which I have just drawn a line. So I'm now drawing the open set which is complement to this line. Now you see this open set is again huge. So now you can see that open sets are giant. So Hausdorff topology is not usually possible in this case. So if you take any 2 open sets, they are going to be so big that there's bound to be intersection. So let me write this down. So it's not usually Hausdorff because the sets are so big. Similarly in A1 you see you take a single point and draw its complement, that's another point, draw its complement, they are going to intersect. So now on these closed affine sets we define some kind of a topology, which topology we will call the Zariski topology, and which will be defined by these closed sets. So on this slide we verify the topology. So we verify the topology for closed sets. So notice that mostly the definition for topology is given in terms of open sets, but here we verify it in terms of closed sets. So we modify the definition accordingly. So we are talking about Zariski topology on the space AN. So first is the null set is part of the topology. It is simply defined as a solution of the equation 1 equals to 0, and the entire space on which we define topology, that is ANK, this is also a closed set because it is defined by the polynomial 0 equals to 0. Now we'll say arbitrary intersection of closed sets is closed. So where each ui here is a closed set. So this arbitrary intersection is closed, where each of these ui is closed. So what is this ui? Now ui obviously is a closed set, so it is defined by some collection of polynomials. So for example, say u1 is defined by two polynomials, f1 and f2, and ui is defined by, this is nothing but set of points in an, and we have this collection of polynomials which we write as fij. The first index stands for the set ui, and the second index stands for the collection of polynomials which define the set ui. So we have this ij specific to the set ui. For example, u1 just could have two polynomials, f1 and f2. So what would intersection be? So intersection would be you throw in all the polynomials defining all these ui's. For example, if u2 is defined by say three polynomials, g1, g2, g3, and u1 is defined by f1, f2, then intersection of u1 and u2 is collection of all these polynomials, that is f1, f2, g1, g2, g3. So that is what I'm essentially going to write as the intersection of all ui. You have taken all these polynomials which define individual ui's, and then you throw all these polynomials together. So again, intersection has to be defined by all these polynomials which individually defined each of these sets. So intersection is again closed because it is defined by polynomials. The third one is that if you have two closed sets, say x and y in an, then their union is closed. Yeah, then the union of these sets is closed. So you start with set x, so you take the points of an, you put fix is 0, yeah, for all I belonging to the index set I, and then you again define another set y. Again, you have to define the points on which the polynomials vanish. Basically, you have to define the polynomials. So these polynomials are given by gjx, and they vanish on the set x element of an. So what is x union y? So the claim is x union y. So we have to show that x union y is nothing but the product. So it is product of fi gj. So this is what we have to show. So obviously for all I and for all j. So let me write down what we have to, this is what we have to show. So the first direction is easy. You take a point P in x union y. So P either belongs to x or it belongs to y. So this implies what? This implies either FIP is 0 or GJP is 0. So we just fix FIP is 0. So that would imply that, you know, this product when evaluated on point P will also be 0 obviously. Multiply something by 0, you get 0. The other direction we will prove by contrapositive. So F does not belong to x union y. So P does not belong to x union y. So P does not belong to x. and P does not belong to Y. Yeah, so then there exists some polynomial which does not vanish on this point P. Yeah, so we have say two polynomials because P is not contained in X and P is not contained in Y. So we have these two polynomials Fi and Gj, which do not vanish at P because P is not part of X and Y. Thus their product also does not vanish on, so the product does not vanish on X or Y precisely because K is a field, so we are in an integral domain, so there are no zero divisors, so their product is not going to be 0, and that proves this. So now I want to talk something about ideals. So you have this bunch of polynomials, say f1, f2, f3. So this are polynomials, or you can say elements of a ring R, or polynomials in the ring, say k, x1, x2 all the way to xn. So the ideal generated by these elements is of the form like this. It's just a summation. Yeah, where each AI is also element of the ring. Now I want to make an important remark, and that is why we have changed the color to peach. So look at these polynomials f1, f2, f3, all of them. So all of these polynomials, say they are elements of they're all polynomials, so they vanish on some algebraic set X. Yeah, so this X lies in AN, so we can say these polynomials are like lying in the ring k, x1, x2 all the way to xn. So then anything which is generated by these polynomials, so all these polynomials vanish on an algebraic set, so the ideal generated by these polynomials also vanishes on the set X, because after all the ideal will be the summation as I have mentioned above, and when you start evaluating the summation at the point P lying in set X, the summation will vanish because each of the elements vanishes. So this is what ideal of X is. So this is a collection of polynomials f lying in, which I have said before, k, x1 to xn, such that fx is 0 for all x lying in the bigger set. Yeah, so for all points in bigger set X. So sometimes we write x element of X or p element of X. So let us give an example. So you define the algebraic set as the intersections of, say, a circle and a line. So set of all points of this plane such that we have these two equations which are satisfied. Yeah, so best is to draw a figure and see how it looks like. So first we will draw the x and y axis. Then we draw the circle first. We follow this up with a line. And here we have the point of intersection. This is the point of intersection. And this is what represents this big set X. Yeah, so the x consists of just this point. There's only point 1, 0, which is the solution of both these equations. So I've drawn it geometrically. You can solve this equation, put x equals to 1, and you will have y square equals to 0. That would imply y is 0. So the ideal associated with it is x minus 1 comma y. So the point is 1, 0. So now you can see any elements generated by x minus 1 comma y would be 0. Our guiding philosophy is like this. You take an algebraic set x, associate with x an ideal in x, and then we define something called as the ring of regular functions. So this is written like this. So you have this polynomial ring. So we are taking this algebraic set in an. So you have the associated polynomial ring k x1 to xn, and you modulo out with the ideal of the algebraic set. Now rings of such type are called K algebra of finite type. So this OX is called ring of regular functions. It is also called affine algebra of X. Sometimes it is also called coordinate ring of X. Yeah, but rings of this form where you have K, x1, xn, and then you modulo out with the ideal or just leave it like this, they are called K algebra of finite type. So OX is an example of K algebra of finite type. So this is important, and therefore I'm going to write it in red. So the guiding philosophy is this. You're given a set x which comes from the polynomial equation. You associate it with that set x an ideal, and then you construct a ring, and you call that ring as ring of regular functions. And this is important because later on we will use this again and again. Specifically, this will be useful in sheaves. Now our next purpose is to connect these ideals I. We link up these ideals I. So this I is linked up with affine algebraic sets. So first what we do is we fix a set of polynomials. Yeah, so let us denote this set by T. This is just a set of polynomials. So it is a subset of this kx1 to xn. So you just take a bunch of polynomials, and let us write this kx1 to xn as a, just in case we want to refer it again. Yeah, so we will write it as a. So the affine algebraic set we are going to rewrite as v of t. We can also write it as z of t. So zeros of t is the notation in Hatcher. So what is it? It is just the set of all points of Kn where these polynomials in the subset T vanish. So I'm just rewriting the way we wrote the algebraic sets. So now I'm writing it as v of t. So just a collection of points on which all the polynomials which are in the set T vanish. So what have we done essentially? We started with the space X. We put an ideal on the space X. Then we are applying V to it and seeing where all the polynomials in the ideal of X vanish. So what did we do? We started with the space AN, ended up with polynomials, and then we went back to space AN. And this is the story. So now we want to just quickly summarize the properties of I and V. So first two properties are fairly obvious. So I is the ideal and V is the zeros. So the first one is if we have this subset of polynomials, yeah, T1 contains some polynomials and T2 contains all polynomials in T1 plus extra polynomials, then we have this reverse inclusion. V of T1 contains V of T2 precisely because zeros of lesser polynomials, like as you add more and more polynomials, the zeros keep on decreasing because now all those polynomials have to vanish on certain points. Similarly for ideals, so if your set gets bigger and bigger, then so your set is getting bigger, so the ideals, the polynomials vanishing on ix1 would also vanish on ix2, because x1 is contained in x2, so obviously all the polynomials will vanish on x1 but obviously vanish on x2, and that's how we have the reverse inclusion. So this is the equality which we have to show. So you take the set x, then you make an ideal out of it, then you compute it 0 and you get the set x back. So one inclusion is pretty clear. Yeah, so this is because you take algebraic set x, then obviously when you compute not only the polynomials but the entire ideal generated by those polynomials, now that would obviously contain set x, because the ideal is the linear combination of all those polynomials, so you're adding more and more zeros to it because you're adding linear combinations also. Conversely, if x is equal to variety of v of I or zeros of I, then ideal of x is contained within this ideal I. Yeah, so ideal of x consists of polynomials which vanish on set x, and zeros of I also consists of polynomials which vanish on set x. So now you apply the v function to it. As you know, v is inclusion reverting, as we saw in 1. So we get this inclusion reversion. Where v of I is x. So that we have now proved both the inclusions, and therefore we have the equality. There is almost nothing in 1, 2 and 3. You just need to draw some pictures and write down the polynomials and convince yourself. This just looks complicated, but it is not that difficult. So now we want to go the other way around. We start with the polynomial, we end up polynomials which are like collection of polynomials which will generate the ideal. We go to an, get the zeros of the ideal, and then we go back to the polynomials. So now we have, now I is obviously included in I of vi. Now for all these inclusions, the best way to prove them is through contrapositive or by contradiction. Say take a polynomial which is not in I, then obviously that polynomial will not be in I of vi. So that is the way it is. That is the way this inclusion process, proof of for inclusions will be clear. So here we do not have seen the case 3, we had an equality. Here we do not have an equality. And that is because variety of I could be extremely small. Yeah, so for I, which is a subset of I of vi, vi could be really small. For example, if you have something like x squared plus y squared plus 1 and R2, obviously the solution set is null set and everything vanishes on the null set. So the ideal associated with the null set is the entire space. So obviously we have the inclusion, but we do not have the equality. Again, the inclusion will be clear. You can easily prove the inclusion by using contrapositive. If a polynomial does not belong to I, then automatically it does not belong to I of Vi, and so on. Second is, suppose ideal is equal to x square. Then what are the zeros of x square? It is nothing but the y-axis. And then I of Vi is y-axis has to be generated as x equals to 0. So you have this like x, but this strictly contains x square.